In this video, I'm going to discuss about the resolving issues in pressure-based solver and parallel mode. And right now, I'm using the ANSYS 2020 release 2. And the softwares inside ANSYS are used are the Fluent and ICM CFD. And the case I'm solving is NACA 0012 3D airfoil with a 1 meter chord length and 0.3 meter span, which is very standard in literature. And Reynolds number is 3 million. And you can find data on NASA website in book of theory of wing sections on this Reynolds number, and also at the 6 million and also at 9 million. So this is a very standard case also for NACA 0012 aerofoil. And the hexagon meshing was created in ICM CFD, and number of nodes are more than 1.2 million nodes, and the Y plus were ensured to be less than 1 everywhere. So to ensure it, I have my own Y plus calculator, which is based on these correlations for CF, and from CF we calculate the wall shear stress, and from wall shear stress we calculate the friction velocity, and that will go into the Y plus formula, which is over here. So from Y plus formula we can get the first cell height in this way, and so we need the Y plus value or the required Y plus value, which is the 1 here, and the friction velocity, which is mu t or mu tau, and the viscosity, which is the standard value 1.79 10 to the power minus 5, and the and density, which is 1.225, which is for the sea level. And from here we get the value as 0.5087, and I put the value as a 0.509, but this is making still, this is giving us the Y plus value less than 1 everywhere, and the maximum value I am getting is the 0.9. And for all solvers, for all settings, for all cases, I am going to run the essay turbulence model. So there are 5 cases, and 5 cases they are implementing the essay turbulence model coupled with pressure solver, incompressible viscous, hyperinitialization, and second order scheme for the pressure, and for momentum we have second order upwind scheme, and for turbulence also we have the first order upwind scheme. And these are the 5 cases. The first case was my natural choice of cases, and I used to run the Fluent in the pressure based mode for the most of my cases, and especially when the flow is not highly compressible. And the version is the 2020 release 2, and since my computer has a 4 cores, so I'm using 4 cores here, and I think that for 1.2 million nodes the 4 cores should do the pretty good job. And second case, once we had the issues with the first case, I will show you shortly. So I run this case with the 1 core only, same case, and I found out that this is solving the issue. It means that the problem was in the parallel software, in the parallel code when we are running the pressure based solver. So then I realized that this might not be the issue with the pressure based solver. Maybe this is something else. So I launched Fluent 2019 release 3 with 4 cores also, which is same as the case number 1, but the previous version. And so since we cannot open this file, latest version file into the older version file in the older version Fluent, so therefore I had to start from scratch. So we have the mesh file, which we exported from ICM CFD in MSH format, and MSH format is the standard format for the Fluent, and it is the standard format since the Fluent release 6. So this file can be read into the Fluent 6 up to the latest version, which is Fluent 2020 release 2. And this solved the problem. It means that the problem was not in the pressure based solver in the parallel mode, but the problem was something has to do with how the mesh was partitioned in the parallel solver. It means that the automatic partitioning is not suitable for pressure based solver in Fluent 2020 release 2 with the 4 cores. And definitely when we are as the science is progressing and so the simulations, so we are going with heavier problems. So heavier problem means we need to have the more number of nodes, more finer mesh, and this means that we must use the parallel processing, otherwise we cannot solve the case on the 1 core. So then I use this case 3 file, which is the Fluent 2019 release 3 file with 4 cores, and I open this file in the Fluent 2020 release 2 with the 4 cores. So just only difference that this file was saved inside Fluent 2019 release 3, and it means that partitions were also created in that software, in that version. And again, we have no issues at all in the new version of Fluent 2020 release 2. It means that the problem was not in the pressure-based solver, not in the parallel mode, but the problem was in the way the mesh is partitioned. And so I redefined the partitioning in 2020 release 2, and this also solved the problem. So the default partitioning is creating problem in the Fluent run for this case. So as we refine the mesh, so it start to make the very strange type of a weird type of partitioning, and this is causing problem. So let me show you these things quickly. So you can confirm that via the coupled solver SA model is used, and we initialize. So on the first case, I will show you that every case was initialized from the scratch. So every case will run from the beginning. So that we can be sure that everything is all right, and there is no effect of anything else on the simulation. And now we run the calculations. So just hit on the calculate. And now you can see that from the beginning we have the various warnings and messages. The one of them is the stabilizing pressure coupled to enhance linearness, solver robustness, negative net in number of cells, and so these errors are there, and later on the error for reverse flow will occur also. So these things are happening here in this is the first case when we run the case in pressure based solver and the parallel mode with a very fine boundary layer. So you can see that these warning errors are there, and if I click on these two signs which are shown here, so we have the warning the load is imbalanced and the memory utilization is very high or imbalanced. And okay, so this is okay. Okay, next thing is that we want to see the contours of y plus. So the y plus should be varying with the velocity. So high velocity, high y plus value, and low velocity, low y plus. But you can see now that this is not happening in this case. This is very imbalanced type of the y plus values, and the y plus values are very higher, even though we didn't run the case for the longer time, but still you can see that we have right now it's 170 value right now, maximum y plus value, and minimum y plus value is 1.51. And but as you see in the Excel sheet that we ensure that the y plus value should be less than 1 everywhere. Okay, so now the second case is, and also I want to show you how the mesh is partitioned. This is very important, and later on you will compare these cases again with the other cases here. So this is the partitioning. It is done by the Fluent right now. And for second case, again we are going to open Fluent. And the only change I'm going to make is that I'm going to run this case now only on the one processor, that is case number 2. So I'm running the same case, same settings, and the same solver version, which is 2020 release 2 version here. But only difference is that now I'm going to run this case instead of 4 cores on the 1 core. So 1 core means that we don't have any partitions at all. So read case and data file for the same file, which is this file here. And if you take a look on the report quality, the orthogonal quality is 0.05, which is pretty higher than the minimum requirement, which is a 0.01. And the same method is used coupled second order pressure, second order upwind scheme for momentum, and all same settings are there. And again we will run this case from the initial condition, and you can, if you take a look on the contours for the y plus value. So I don't remember that this is my old file which I just ran this case, or this is some saved file. Okay, this is already solved case here. So what I'm going to do is that I'm going to save this case which we have the errors. Okay. So I will save this case in G drive. So new name, I put name as a NACA 0012 only. So this is with the error. So I can save this file. And I will open the same file in the same version of Fluent but with only one core. Okay. So go to file and read cache and data file so that we can be sure about that everything is all right. So there shouldn't be any doubt here. So I just want to remove that doubt that we have something already a saved file, or this is a half cooked type of the thing. So I'm just running this case from everything is from scratch. Okay, so open this file now again. And the only thing is that we have the only one core now in the same version of Fluent 2020 release 2. And again display the y plus values. So you can see that this is the same case which we saved in the previous case number 1. So same file, and I'm reading this file into the new version. Alright, so now I'm going to initialize the solution. So on the same case with the errors, everything, the only thing is that I'm going to solve this case with the single core, and then you will see the difference that what is happening here. Alright, so I will save this case file and data file as case number 2. As you can see that we have the name as case 1, and then we have the case number 2, so that you can identify. I will upload these files in description of this video, and so that you can download this file, you can see them yourself and run them, and you can confirm the things we are seeing in the video. And again click on the run calculation and click on calculate. And you can observe that from the beginning the case is running very smoothly, and the results they are dropping very nicely, and the drag coefficient and lift coefficient, they are also converging very nicely within the range, and I don't see any issue at all here in this case. So the only difference here is that I am running this case on the 1 core and previous case was on the 4 core. So the parallel processing is somehow making the issues, and later on we found out that this is issue with the partitioning done by the Fluent 2020 release 2 version. And the results they are converging very well, and within the few iterations you can see the drag is and lift coefficient they are converging very nicely. And at the moment we have the drag coefficient which is same as we have for the previous cases, so that is around the 0.009, and the actual value is low is the 0.009006, which is this is a very common error in turbulent simulations, because this particular Reynolds number and this airfoil has some region in the laminar flow. That's why, because we are not predicting that region, so we are getting the higher value of drag coefficient. And if we stop solution and check the y plus values, you can see that these y plus values are behaving very nicely, and if you compare with the first case, you can see the difference. The y plus values are changing from 0.9 as a maximum value, and the minimum value is a 0.2. And at the extreme zone we have the lower value, and then maximum values on the two sides of the aerofoil as the flow is accelerating. And once the flow has accelerated and then it's decelerating, so we have the lower values of y plus value as in the relationship to the velocity values. For third case, I have to open the Fluent 2019 release 3, And since I cannot read the old mesh files, so the old case files which are in the new version, so I need to create the case from scratch with the mesh file. And settings are double precision 3D and 4% same as case number 1. And now this is case number 3 here. So this mesh file and the number of nodes are same, which is around 1.2 million are the higher value. So 1.23 million exactly. Okay, so I will choose the SA model first, and energy equation will remain closed off because we have the incompressible flow here, and material properties are density is 1.225 and viscosity is 1.79, and boundary condition is the velocity value, which is and this value is 43.836, and you can also put the as a magnitude direction, so we get the x component as a 1 and y and z are 0. So this is correct here. And the next thing is that we have to initialize the solution. Before that, we have to set the monitors, and they should be very, very low values. So in the previous cases, you can observe this is set to the very lower values here. And also we need to set the report definitions for drag and lift. And after solution initialization, we run the case. Again, the few iterations so that we can have the idea about the solution. And hit on calculate. Case number 3, which is Fluent 2019 release 3. And we are solving this case with a 4 core. So again, this case is running very smoothly. So might be you are wondering that why this case is with the 4 cores is running smoothly with everything same, except that we have the different version. But why not in Fluent 2020 release 2? This was my question as well. So the answer is you will get at the end of this video. And I will see the Y plus contour plots. And again, the Y plus value is within range, which is 0.9. And it's the same distribution as we have seen in the case number 2. So it means that the problem is not in the coupled pressure-based solver with the parallel processing, but the problem is the way it is making the partitions. So now let's take a look on the partitioning on this geometry, and you will see that this is how the partitioning is being done for the Fluent 2019 release C version. So here we have the very nice partitioning, and there are 2 blocks on the outlet, and the 1 block is on the upper side, including the few portion of leading edge, and then 1 block is on the bottom side. So this is very nice type of the distribution and very smooth. So I guess this is difficult to create manually, but this is done very pretty fine in the Fluent 2019 release 3 version. So I will save this case file with the new name, which is the case number 3, and you will get all these files with you. So case number 3 here. Case number 4 is that we are going to read the mesh file, the case and data file we saved in the case number 3, in the which is we saved file in the Fluent version 2019 release 3. And we are going to read that file, those 2 files, in Fluent 2020 release 2. So it means that the partitioning is done in the 2019 release 3, and the only solution is being done in the 2020 release 2. But before that, I want to show you the case file we have for case number 1 and how the partitioning look like. The one thing is that I cannot see the partitioning, so this is only single partition here. So I think the partitions are deleted from the that file, or might be some error here, so I cannot display these partitions right now. But I can show you the results which are shown here. You can see here. and so we have a very high plus, very high y plus value. So I'm going to, I think that we have opened the wrong Fluent, and it should be with the 4 cores. It should be with the 4 cores. So I'm going to open the 4 cores. Okay, so now we have the 4 cores, and I will read the first case file, which is case number 1. And you can see the partitioning done in this file. And now I'm going to read the case number 3, which is the case number 4 is the case number 3, but the run will be done in the new version of the Fluent. So I'm going to read the old version file, which is the Fluent 2019 release 3 file, and the partitioning was done very nicely in that case. So in my point of view, that we should stick to 2019 release 3 version at the moment, unless we get the solution for this problem. And this is a partitioning done in the 2019 release 3. Although you can make your own partitions manually, but I think that will be cumbersome, and at least as far as the Fluent part is concerned, so I don't see that any changes or any improvements are done in the Fluent, the new release. So there's no point to be working with the old version here, with the new version here. So you can pretty solve all your cases, including multi-phase, turbo machinery in 2019 release 3 very easily. So again, I will initialize the solution from scratch. So only difference is that we are reading the 2019 release 3 version file into 2020 release 2. So the partitioning is done in the old version, and everything else is same except the version number. And also I have one more observation, that this step, which is very fast, was very fast in 2019 release 3, and it is taking long time in the 2020 release 2. So even in initialization is taking more time. So I guess that 2019 release 3 is the faster version. It has more stability. So you should revert back to that version right now. But maybe in the future, when we have some these bugs are removed from 2020 release 2, then we can move to the new version. Okay, then I will click on the calculate. For case number 4, solution is now done for the 100 iterations. Now we can take a look on the results, especially y plus values. So choose the contours of turbulence and then y plus, and uncheck option for global range and choose the NACA 0012 airfoil. And you can see that now again we have the same type of distribution as we did in the case number 3, case number 2, and that is we have the lower value on the leading edge, then values increasing, and the relationship is same, that the y plus value is increasing with the increasing value of the velocity and decreasing with the decreasing value of velocity. So the same trend is followed as we had in the case number 2, case number 3. And so I can save this case number 4. And again, now the case number 5 is that we are going to use the case number 1. And the only thing is that we are going to make the partition ourselves. So from the file, read case and data. And I'm going to read the case number 1. So instead of using the default partitioning, which is done by the Fluent 2020 release 2, we are going to make the partitions ourselves manually. And here I will save first the case and data file with a new name, that is the case number 5. Again, I will display the mesh with the partitions, so we can be sure that this is the correct file with the problems. So this file has the problems in 2020 release 2, and so the issue is basically is the partitioning done by Fluent automatically. So what we are going to do is that we are going to, first of all, we are going to create the 4 registers, and that is done from the domain and refine coarsen. And so this is basically is a made adaptation panel here, and that is used for traditionally this is used for making the mesh refinement and mesh coarsening. And also we can have the 2 registers or more registers. Register is basically is a collection of the some mesh portion. And so for multi-phase simulation, let's say we have the air and water, so we can initially, let's say we have some level of air and water in the domain, so we can also use a register to define the boundary conditions, the initial conditions for the water and the air level in the domain. And third application is we have for the partitioning. So from cell registers, I can click on new and region, and here I am going to make the 4 regions. One is on the leading edge to trailing edge, and that is on the upper side only. Then on the up to the trailing edge and the upstream side on the bottom side, then the 2 sides on the downstream side, upper and lower. So on the first register, I am going to make x maximum, x minimum. I know x minimum is around 19 or 20. So to be sure that everything is included here on the left side, I am putting value as minus 25, and x maximum is the one which is up to trailing edge. And the y maximum is the 25, which is from the trailing edge to the upper side, and the z maximum is the 0.3, which is the domain extent in the z direction. So click on save and display. This is the portion we get with these values for coordinates. And the register 1 would be the on the bottom side of the domain, which is the same as the same region but on the bottom side. So I would put the minus 25 y maximum and save display, and then I will change this value of x maximum, x minimum to 1. So from starting from trailing edge up to the last point of the domain, and let's say put the x maximum as 55. So and the y minimum I will keep the same, which is the minus value, and in the next one I will put the value as again positive. So first, second, third, and then fourth, and click on display, save. So this portion is selected now, and the last one is in the positive y direction, and region name is the 3, and click on save display. So we have the 4 portions. One is on the leading edge and upper side, second on the leading edge up to the trailing edge on the bottom side, then on the bottom side the downstream side, then on the upper side on the downstream side. So now we have these four registers with us. And again I display the partitioning right now at the moment, which is like this. So I will go to the parallel tab here, and from here I will click on the partition load balance, and here I can print the active partitions which are shown here. So we have the 4 partitions. They have the equal number of nodes here. So I'm going to print stored partitions. So stored partitions are in this way. So I will click on the use stored partitions here. So let's see what happens. So again I display and click on selected zones and register to partition ID and partition. So we have to use this option multiple times. So again print active partitions, they are still same, and use stored partitions. Again display. So they are changing little bit. So I would be choosing these registers with me, which are the 4 regions here, which are we got from the mesh partitioning, and then the third one. Okay, so I will print again the active partitions, which are now different. Now these are this one, and so again I display. So print stored partitions, which are now we have the only one partition here. You can see here. So I will click on the use stored partition again. And as soon as I click on display, I cannot see any partition here. So now again I will click on the partitions and click on display. Okay, so print active partitions, we have only one partition. Print stored partitions, we have these 4 partitions. So I will click on use stored partitions here, and as I click on the store partition and display the gate, this time this worked. So now we have these 4 partitions, And so I will take a look from the close. So you can see this is the partitioning done by the manually by the from these partitions, and this is how this will look like. And it's a different than the 2020 release 2. It's automatic partitioning. Also, it is different from the 2019 release 3 partitioning. The next thing is that we are going to initialize solution again from the initial conditions with the help of the hybrid initialization. So we are done with the hybrid initialization, and now again we'll click on the run calculations and we run the case for maybe 100 iterations. And you can see now this is the case number 1 actually, case number 1 with the manual partition. So we had the issues in the case number 1 because we were getting the stabilizing the couple solver, and the nut is basically is the turbulent quantity for SA model, and it was negative quantity on the many cells. But after making the partitions manually, you can observe here that this problem is gone. So now we can conclude that the problem is basically is not in the 2020 release 2 version, it's not in the parallel solver, it's not in the pressure based couple solver, but it is in the way it is making partitions on its auto. So either there are two solutions: either you should make the partitioning yourself when you get this error, or you can revert back to 2019 release 3 if you still have the access to that version. But in my point of view, the best bet at the moment would be that you should go to the 2019 release 3 version and wait for some update to resolve this problem in this version of the Fluent. Okay, so 100 iterations are completed. Now I will write this file as case number 5. So case number 5 here. So I just want to be sure that we are running the correct version. Yes, this is 2020 release 2. And so first of all, I'm going to display Y plus contours. On NACA 0012 airfoil. And again we have the same Y plus value, which is 0.9. So it means that the problem was not inside the Fluent 2020 release 2 or in the parallel solver or in the pressure based couple solver, but the problem was in the automatic partitioning done by that version of Fluent. So at the moment I guess that either you should manually partition your grid by yourself whenever we have the very fine mesh. This happens sometimes. So for the larger boundary layer region, I didn't see this problem happening here. So this might be is happening in some few cases, and so either they solve the problem, the answer solve the problem for these typical cases. So until then, you can continue using the 2019 release 3 version, which is pretty same as compared to the 2020 release 2, and I don't see that there are much changes in the both versions. So 2019 release 3 is more stable version as compared to the 2020 release 2 in terms of especially this case. And I cannot comment on other cases, but this is what I have seen in this case.